entropy. Entropy is a measure of information. And I don't think this is supposed to be in this course at all, but it has to do with balanced binary trees, and this section is called balanced binary trees, so that gave me the excuse to put it in. All right? All right, so entropy, I think everybody should have some sense of, and, and this first guy, he came up with a definition of entropy that had to do with physics and disorder, right? And his definition was, if you knew the macro description of your material, say you knew it was a crystal, then how many ways, how many micro ways are there to organize the particles? And you take the log of that, and that's your entropy. So this guy is highly ordered, so you know where the particles are. So it has a small number of places the atoms can be, so it has low entropy. But here, it's a gas, so everything's flying around, so it has high entropy, right? And low entropy, higher entropy. And one of the laws of thermodynamics is that entropy always goes up. And somehow that's related to time. Why does time go forward? Some people theorize, well, time is a byproduct of entropy. So it's all very interesting. So how does this come into it? is this baby here is going to want to communicate. Now we're moving into Shannon's entropy, right? Shannon is, right, so I guess why do we take the log of the number of possibilities? One is because the math works out nice, and it also converts from a number to the number of bits, right? So if there are capital N ways to organize this stuff, then it's, anyway, let's get on to bits, because that's what we all care about. Here's our problem at hand. Shannon came up with the idea of Shannon's entropy, and here we have a baby, and the baby has randomly chosen a toy, and there's going to be a probability distribution with which the baby chooses the toy he likes, and he has to tell Shannon the toy. So he says something, and Shannon says, I don't understand you. So Shannon wants him to use the minimum number of bits to communicate which toy he has, right? So the baby gives a bunch of bits, and Shannon says, that's great, but we need a code so I know which one you're doing. And, and so this guy here, this toy has code 01, and so the baby says 011, and we know it's the truck. But do we know it's 011? What's the problem? Well, instead of it being the baby saying truck, the baby might be saying potato head followed by transformer, right? Right, because you see it's this code followed by that code. Right, so that's a problem. So the way we fix that is we have all our codes be what we call prefix unique, and we're going to describe it by a tree. And that's why it's in this section, because we're talking about trees, and everybody loves trees. So here's a tree that's going to describe a code. All right? Everybody with me so far? So how does it describe a code? Well, the baby says a bunch of bits, and we follow the path. It's a binary tree, so every edge is labeled 0, 1 coming out of every node, and you can follow the path down, and we get that the baby is saying duck, which is quite reasonable for a baby to say, right? Everybody good? So what's better about this code is that the baby can put lots of bits, and the first bit gives you the duck, right? You follow 0, 0, 1, 0, 0, and you get duck. And then Shannon says, oh, hey, that was a duck, but we got more bits. And what do we do with the more bits? Right? We start right back at the top of the the tree, and we follow 0, 1, 0, and we get a lion. Right? People see that? And that brings us to there, and then we have one more bit, which gives us the dog. Everybody following this code? And it kind of, here we're supposed to be about data structure. So here's a data structure for encoding and decoding. It's the data structure. So we're in the data structure course, so we should be doing this. Everybody good? Yeah? Well, one more 0 at the end, then it would be a partial code. And Shannon would say, hey, baby, you kind of went to sleep in the middle of a code. Right? Does that make sense? All right. So now you might notice that this tree is not a balanced tree. Right? And because it's not balanced, some codes are shorter than other codes. Right? To say dog, you only need one bit. And to say this car, you need to say a lot of bits. Right? And so you might say, well, why are we doing that? And, right, that's what I just said. Right? So here's our problem. I'm not sure how much probability theory you've learned, but my sense is that you guys don't learn much of it. Have you guys done any probability theory? He has. Is anybody else? You know about you flip a coin and you flip another coin and you do some probabilities? Probability theory is great, and you should learn some. So if I say anything, this is going to be about probabilities. So if I say anything about probabilities you don't know, what are you supposed to do? Guess. Put up your hand, right? All right, so here, this is probabilities. These numbers down here in green at the bottom, I can't see them, but can you see them? Yeah, they're green numbers at the bottom. Those are probabilities, right? They're numbers between 0 and 1. And if you add up those numbers, it'll add up to 1, right? And so you can think about it as a bunny-shaped dice where I roll the dice and I get one of these toys. And on average, if I rolled the dice 100 times, then I would get this car 2 of those 100 times, right? And I would get this transformer 2 of the 100, and the potato head 1 of the 100, right? And I would get the dog almost half of the time. Everybody understand what the probabilities are? Everybody got that part? Yeah? All right. All right, now we also have code lengths, right? So the dog has a code length of 1, where the slinky has code length 1, 2, 3, right? So each object here has a code length, right? Does that make sense? Now, we want to say, given our code lengths and given our probabilities, we want to calculate if the baby were to choose a random toy, what is the expected length of the code? All right? And so you have to know how to calculate expectation. And the way you calculate expectation is it's like an average, right? What is expectation? It's kind of like, well, what's your average, right? But it's not a straight average. It's a weighted average based on how often it happens, right? So you can imagine, actually, if we were to do this 100 times, and if we wanted to average, we would add up the numbers and divide by the number, right? We divide by the number of things. But here, we could say, if we do it 100 times, then this guy happens twice. So pi is 0.02, but why is it twice? It's because it's 0.202 times 100. It's how many, right? So we take, well, it happens twice, and we multiply by the length of its code, and we add up, and that'll be the average number of code lengths when we do it 100 times. We divide by 100 again, and you get this equation. Right? Does that kind of make sense? Right? You weight each length by its probability. And another way of saying that it's a nice weighted average is that the PIs sum up to 1. Right? So for example, suppose all the L's were 1. Right? Then the sum would be 1 because the PIs sum up to 1. And, well, it's great to know that if all the L's were 1, then the average L would be 1. Right? So you want that to kind of work out. And that's partly where we use the fact that these are probability and they add up to 1. Everybody kind of get where you get this expectation? Yeah? All right. So here's the game we're going to be playing. We decide ahead of time, right? Before we play this game, we had to come up with a code tree. Right? So ahead of time, we know the probabilities that the baby's going to choose these various toys. So we know the green. And our goal is to choose the code lengths to minimize the expected expectation. Right? Does that make sense? And so what is our problem? Our inputs are our probabilities, and our solution is a Hoffman code. Right? It's one of these trees. And which tree do we want? We want the tree that minimizes these expectations. All right? And, right, so our goal is, given the probability, find the code that minimizes the expected number of probabilities. And we're going to use a greedy algorithm. All right? And you don't need to know all the details, so we might flip through this quick. We got these objects. What we're going to do, we're going to use a priority queue. All right? We're going to sort these objects by their priority. Right? They're already sorted by their priority. And we're going to take the two objects with the smallest priority, and should they have the biggest code or the smallest code? They should have big codes because they don't happen very likely. So we're going to start building a code on them. We're going to build a little tree on them. That's going to be part of their code. But now the probability that one of these happens is the sum of their probabilities. Right? So this tree, this little tree now happens with the sum of these two probabilities. Right? We got the probability. Where have we got our mouse then? This probability plus this probability is that probability. Right? Everybody with me here? Well, this is 0.015 and 0.01. I think it adds up to that. Right? I could have had it wrong, but right. So now we repeat the process. But this is a priority queue. So remember, these two objects are going to bubble up in the heap. Right? So we put them where they belong in the heap. Sorted. And then we take the next two guys with the lowest priority and we put a little thing on them. Right? And we move them where they are in the heap. And we keep repeating this. People kind of follow this? You take the two here. These two have the smallest probability. So we put a little tree on them. And now they have a bigger probability, so they bubble up as a unit. Right? And so now we put a tree on those guys. And now this one and this one have the lowest probability. So we put a little tree on them. Right? You following this? And you keep going. You keep going. And then eventually we have our tree. Right? And that's pretty much all we wanted to say. We could get into more about what the probabilities are. And here, definition of entropy. Let me just tell you, If the probabilities are these p's, then an object with probability pi, well, if it has probability, if all the objects had probability pi, then there would be 1 over pi of them, right? So, and if you had this many objects, then how big should their codes be? Well, if you have n objects, their code length should be log n. So that's why we take the log here, and that's called entropy. And entropy comes up all the time, all right? In fact, I was on somebody's master's thesis once, and what I did was I flipped through their master's thesis because I don't like reading, and I found the math. Oh, that's math. Oh, that's entropy. I like entropy. And so I asked him during his defense, tell me about entropy. And do you know what he knew about entropy? All right, so we got more about entropy, and that's good. Then we got splay trees, which are in different types of things, and we're done trees. Everybody good? Partly we're moving fast because you know we're a week behind. So that just help us catch up. Now it's time for a break, isn't it?